let you know what, but you can guess, okay, from our lecture. Without further ado, allow me to present lecture 7. Hmm? Oh, yeah, here it is. Okay, on dimensional analysis and modeling. Right, okay. So here we are. I've uploaded the, okay, I've uploaded lecture notes in Elip. Okay, you can have a look. But I would ask you to give your fullest attention to the lecture notes, okay, that we are sharing. Okay, chapter 7 on dimensional analysis and modeling. Okay, this is the chapter 7. Just give me a sec. Yeah, okay. Right, this is chapter 7, dimensional analysis and modeling. Now, right, as the naming shows, dimensional analysis, we shall be studying about the dimension, fellas, right? We shall be studying about the dimension as well as modeling because they are strongly related to each other. Okay, so that's why you need to understand the dimension in a bit, that you'll see this one is quite a straightforward concept. But then again, the application later on towards modeling may not be that simple, right? Okay, I'm not trying to scare you, but then again, this is something that you have to take seriously. Okay, we shall study about the dimension, we shall analyze it, okay, from the naming itself, and then we shall do modeling after that. Only after you have understood what dimension really is. Okay, only after you have understood. So that is why in this particular lecture, just this morning, I would like to stress on just the dimension. Okay, just the dimension, right? Don't worry. We'll go through this very thoroughly. Okay, I'll explain to you. I'll give you some examples, and then we shall discuss on the examples. I'm going to give you some exercises we try on, and then I'll share the answer with you. Then I'll give you your present. Okay, right. Chapter 7. Now, these are the objectives. Okay, these are the objectives of chapter 7. Okay, of the textbook. Like I told you, the textbook that we use. Right? Okay. Right. The first objective of today's lecture of chapter 7 is first to develop a better understanding of dimensions. Like I told you, you have to understand the dimension first. Right? When you have dimensions, then you have units. Okay, to address the dimension. Okay, and then we shall study about dimensional homogeneity. This is where it gets quite interesting. Okay, because most of the students, they don't know what this is. It looks simple, but the application is various. Okay, it's numerous. All right, you will see the application of this in order to check. When you do modeling, you're going to come up with the equations, right? Okay, when you do modeling, modeling is basically for you to approximate, okay, the real life thing, right? If you are going to forecast like a speed of a car, instead of like measuring the car itself, like literally, you can do modeling. Okay, you can develop an equation that could represent the whole thing. Okay, so dimensional homogeneity is for you to check whether your equation is valid or not. All right, so this in our lecture today, I just want to stress on this one. Okay, I just want to stress on this one. In fact, it's one of the most important part of this lecture. Second objective of chapter 7 is to understand numerous benefits of dimensional analysis. Right? When when you have understood this, then we shall move on to dimensional analysis. Right? We shall analyze. Then you'll know the advantages, of course, from the usage of dimensional homogeneity in equations. Okay, to check on the validity of your equations. Now, the third objective is to know how to use the method of repeating variables to identify non-dimensional parameters. This is where it gets really hard, right? This is where understand the concept of dynamic similarity and how to apply it to experimental modeling. In other words, it's just modeling. Okay, how to use the concept that we have learned all together and then produce a model. That is what we shall be doing in this lecture 7. Okay, which is on dimensional analysis and modeling. Okay, that's enough for introduction, I believe. Right, okay, dimensions and units. All right, dimensions and units. All right, okay, dimension. This is the definition of dimension. All right, dimension is the measure of physical quantity without numerical values. Unit, a way to assign number to the dimension. You know what, fellas? Allow me to tell you a truth. Yeah, allow me to share with you a little bit of secret. Right, a little bit of secret. Dimension is a measure of physical quantity without numerical values. Unit is a way to assign a number to that dimension. To be telling you the truth, this kind of thing, like the definition, will not come out in a test. So you don't have to bother. Okay, it's just what they call that. We won't ask you to, okay, please define dimension. That is like, I think in the past, like in the past 15 years, yes, you could have that sort of question. Define this, define that. We're not going to do that anymore. So you don't have to worry about the definition. All you have to do is you have to know instead of remembering the names. Okay, you have to know what dimensions are. Okay, right, okay, have a look at this. These are dimensions. Okay, there are 7 primary dimensions, also called the fundamental as well as basic dimensions. Okay, the dimensions are mass, length, time, temperature, electric current, amount of light, and amount of matter. I repeat, there are 7 primary dimensions. Okay, they are mass, length, time, temperature, electric current, amount of light, and amount of matter. Okay, so you just have to remember these. These are the dimensions. And all other equations, like force, for instance, they are derived from the primary dimensions. Okay, force. Okay, what is force? Force, as from second law of Newton, you know that F force equals to M and A, right? Force equals to M A. Now, if you right, okay, maybe you don't understand this, right? I'm just gonna share with you, okay, the whiteboard, right? I'm just gonna share with you the whiteboard. I'm gonna write on something. Okay, we'll do it very slowly, fellas. Just gonna show you. Right, allow me to share the whiteboard first. Share, yeah. Can you see this, fellas? Boleh tengok the whiteboard?
Yes, sir.
Okay,
Yes.
cool.
Yes.
Right, okay. Right, okay, from the lecture, it says F. Okay, this is what given in the lecture. Where is it? Where is it? Okay. This is what given from the lecture. It says okay, this force equals to, what was it again? Let's see, force equals to, in bracket, you have mass, and then a mass length over time square. Length over time, okay, in bracket square. Okay, and then okay, equals to this m, let's see a sec, m l over t square. Okay, m l over t square. Now, okay, this is what we're gonna do today. I would like you to, okay, I'd like you to expand, okay, just for instance, yeah, force. You have force, or in other words, F equals to M A. force, mass, and acceleration. Okay, I repeat, force equals to mass plus acceleration. Okay, now your task in the first part of the lecture is for you to expand the force. Expand the force in its primary dimension. So this is how you do it, fellas. You expand this, okay? Let me show it to you like step by step, okay? F equals to ma. Then you have force, okay? Just like write it down. Force equals to m, which is the mass, okay? You have to write them down in its primary dimension, okay? In its primary dimension, okay? Now you have to remember these are the primary dimensions, regardless of how big the equations are. All right, these are the primary dimension. You have to remember mass, length, time, temperature, electric current, amount of light, amount of matter. So these are the only primary dimensions. So what you need to do now is to expand the force and write it down in the form of this symbol. Okay, in the form of this symbol. Right. Okay, you have force equals to mass over length over time. Okay, why is that length over time? Okay, allow me to show you. Okay, force m. M is already in its original primary dimension, right? Because mass, okay, just write it down as mass. Now, area, oh sorry, it's not area, is acceleration. Acceleration, on the other hand, is the rate of velocity. Okay, rate of velocity. Rate of velocity. Velocity, you have v divided by t. Okay, and you know that v is actually displacement. Displacement, t is already in its primary dimension, right? Okay, v itself is actually the displacement L over t. Okay, L over t. Now, in this case, if you were to expand this and expand everything in its primary dimension, you would have v here, you would have L over t, okay, over the rate of t. Okay, so that is why you have mass in m, L, okay, divided by t squared. Right, ml over t squared. So this is it. Okay, so this is it. Okay, why you're tangled everywhere. All right, okay, right. So you have, this is force written in its primary dimension. So this is the basic knowledge that I would like you to acquire. All right. I know it does look hard at this point. Okay, if you follow me, you just need to expand to whatever that's given to you. Now, it could be, okay, it could be. Now, this one is force, right? What if I give you power? Sorry, pressure. What is pressure? What if I give you pressure? Pressure, and then I want you to expand this into its primary dimension. Write it down in this format. This is power. What if you've got like Reynolds number? Okay, I want you to write in this form. Okay, why do you need to write them in this form? Okay, this is the introduction, like I told you. The moment you don't know this, you're gonna have problems in the Buckingham pi theorem later on. All right, in the Buckingham pi theorem, you're gonna have problems. So that is why we need to expand all the things that you know, expand and then write it down in its primary dimension. Okay, we're gonna try this, don't worry about it. What about H? What about H, fellas? Stands for enthalpy. Okay, of course, you need to expand this one first. P equals to F over area. Okay, now you've got the F, right? You've got the F. Okay, this is the F. Its primary dimension. All you need to do is that this divided by area. Area is meter square. Area is okay. This is, you have ml over t square, and then this one area is actually L multiplied by L. So this one divided by L square. Okay, this one is divided by L square. All right. So this one, okay, Reynolds number, for instance. Now you have to write it down in this format as well. Rho V L over mu. Okay, over mu. So you have to expand this. What is rho? What is V? Okay, V is already in it. Sorry, this one is L3. This one is L. This one is rho. What is rho? Okay, define rho. That you have kg over meter cube, right? Rho is kg. Kg is of course m, and then you have meter cube. Again, you have L power 3, and then mu. Okay, you have to define mu, and then h. What is h? H equal to m. Okay, small h. M is already in its primary dimension, then you have to expand H. All right, we shall see this. Okay, we shall see this. It's actually a way for you to expand the equation. Okay, in its primary format. That is your task for today, right? That is your task. I'm not, to be honest, I'm not going to go any further. I'm not going to go any further than this. Okay, because the moment you have not acquired this, is gonna get very, very difficult. Okay, it's gonna get very, very difficult. I'm gonna share with you why you need to understand that, right? Okay, this that is just some introduction, right? Introduction of what I expect us to do this morning. Okay, you need to understand. If you don't understand, you have to let me know. Right? Okay, dimensions of force. Force equals to ma. Okay, they expand the a into length over time square m. Okay, and they write it down in such a way. Right? How they got this? Oh, okay, in the next slide, right? Okay, first, a dimension is the measure of physical quantity without numerical values, and while a unit is a way to assign them. Okay, you have the length being the primary dimension and the centimeter being the unit. Okay, I think is quite straightforward. Yeah, right. Okay, how to write them in its primary dimension is just use this symbol, fellas. Like I told you, you have the primary dimensions, 7 of them. 1, 2, 3, 4, 5, 6, 7. Mass, length, time, temperature. Time and temperature, don't get confused. Time is a small t. Temperature is a capital T. All right, the electric current, amount of light, amount of matter. But to be telling you the truth, right? To be telling you the truth, I think most of the questions in your case, fellas, will just comprise of these 4 primary dimension, right? Most of the questions, to be honest, right? I'm not saying your test, right? But I want you to give your fullest attention to the first 4: mass, length, time, and temperature. Right? It's quite rare that we use electric current, right? And even rarer, right? We use the amount of light. More and light, we use them in thermodynamics, right? But not so much in fluid, though, right? So that is why I'd like you to give your fullest attention, okay, to mass, length, time, temperature, because as far as your exercises are concerned, I think they will just be within this group. Right, within this group. And don't get yourself confused with the unit, right? With the unit, and then convert to symbol. We want you to write these primary dimensions in its symbol. Okay, have a look at this. You have MLT, T, right? You have MLT, T. Okay, that's the thing you have to remember. Just the MLT and the big T. Okay? In fact, force is derived from this. Okay, you have to expand them. I'd like you to do it systematically as such as this order. Okay, force equals to mass, length over time equals to this. All right, ml over t square. So you have this mlt time, temperature, also t, but big T, small t. Okay, and the units. All right. Okay, so that will be it. That will be it for the first part of the lecture. Now, I am going to proceed with the second part of the lecture, which is on dimensional homogeneity. Right? Just a few more slides. A few more slides. Don't have to worry. A few more slides, then we get down to the question. Right? A few more slides. Okay, because this one is quite strongly related. Okay, the laws of dimensional homogeneity. Every additive terms in an equation must have the same dimension. Do you understand this, fellas? Dimensional homogeneity is that every additive terms in an equation must have the same dimension. Take this one for instance. All right, must have the same dimension, meaning they must, okay, if it is like ml over t2, all the equations must be made of ml over t2. Okay, you have this, a change of energy equals to the change of internal energy plus the change of kinetic energy plus the change of potential energy. Now, where have you seen this equation from, fellas? Where have you seen this equation from? Can anyone tell me? The equation does look similar, right? Can anyone tell me what does this equation represent?
Energy balance equation.
Exactly. Thank you, Elhan. All right. That is the energy balance equation, or the first law of thermodynamics. Okay. Energy cannot be created or destroyed. It can change from one form to another. Right. So that's where your energy balance comes from. Okay. Thank you for the answer. Right. Okay. So we were to prove that all the additive terms. Okay. We have an equation, right? This is an example of equation. You have U plus KE plus PE. Now, you have to make sure, under the law of dimensional homogeneity, you have to make sure that they are of similar dimensions, fellas. You have to make sure that this dimension is the same as this one, is the same as this one. Otherwise, you're going to have something like this. You are going to have something like this. Apple plus apple, how much is that? How much is it, fellas? If you have two apples. That's right. Apple plus apple, you have two apples. What if you have apple plus orange? Would you be able to define this? But would you be able to define this in an equation? You can't. Right? You can't. You have to make sure that everything is apple in the first place, or everything is orange in the first place. If you have three orange, okay, that's fine. Orange plus orange, you'll get orange in the end. If you have apple plus apple, you have apple in the end. But if you just have if you have apple plus orange, it's not going to be apple no orange, right? So it's, you can't do this. Just like, okay, just like giving you another, okay, I'll give you an example. Okay, okay, I'll give you an example. Like again, with respect to the E equals to U. Okay, change of U plus the rate of kinetic energy. Rate of kinetic energy. Now, do you think that this equation is going to be balanced? Do you think that this equation will be balanced? A change of E plus a change of U plus a change of KE over time. All right. This is one way to check that equation is wrong. See, this one, okay, just, okay, if you don't know the dimensional analysis at this point now, tell me the unit for this one. Can you tell me the unit for this one, fellas? Unit for the change of energy? What's the unit?
Joules?
Yes, you have joules. Okay, this one also joules. This one is joule per second. Right? Or watt. How can you add to joule, okay, equals to joule plus watt? It does not make any sense. This is how I check whether the equation is valid or not. You know, the moment you have done modeling, okay, the moment you have done modeling, if you have something like this happening, meaning the equation is, okay, we can simply state that equation is invalid. Why? Because you have one incorrect part of the equation. Because when you develop your own equation, fellas, when you develop your own equation, okay, you will not I'm not asking you to develop your own equation at this point, right? It's too early. Okay. In fact, you have your time. Don't worry about it. Right. When you have equations, okay, when you have equations that you develop on your own, you have to make sure that it's valid. What will be the method that you can use in order to check whether the equation is valid or not? You can use dimensional homogeneity. Okay, homogeneity, right? You can use dimensional homogeneity in order to find out whether your equation is correct or not. In this case, is definitely it's not, right? What I'm showing you is something that is quite simple. But when it comes to modeling of the equation later on, like numerical or experimental modeling, is going to be way more difficult. And this is, you can use this. Okay, this is the benefit of using dimensional homogeneity. That is to find the validity of your equation. All right. Okay. That's it. All right. That's it. Don't worry. We're just gonna have our lectures for a few more minutes. And then we're gonna try some exercises. Oops. Okay. Right. So that's basically what is what it meant by dimensional homogeneity. Okay, dimensional homogeneity. So when you add all the elements of the equation, they must be of the same dimension, which will give you the same unit, right? Dimensions as well as unit must be the same. Okay, I add up, yeah? Okay, the dimensions, not only the dimensions, the units must be the same as well. Because the unit will represent the dimension. Okay, the units will represent the dimension, just like what you've been introduced in the first slide. Okay, so delta E is in joule, this one is in joule, this one is in joule, this one is in joule, so it's correct. Another way of finding out is to expand them. You need to expand them into primary dimension. Okay, you need to expand them in terms of primary dimension. Now, okay, you expand this. Try to expand this, fellas. Help me to expand this one out. Okay, delta U. Delta U is, this is internal energy, okay, is M, the mass, multiplied with the U. U is actually internal energy, okay? Internal energy per unit mass. This is an internal energy per unit mass, all right? The kinetic energy is half mv square, m the velocity square, and then the potential energy, right? And the potential energy is mgz. Now have a look at the equation, fellas. They are not the same. They're not the same. This one is mu, this one is mv, this one is mgz. Okay, how come they will they give the same dimension? Right? Will they give the same dimension, fellas? It's time to find out. Right? It's time to find out. In fact, you can give it a try. You can give it now. You have to expand this one m. You have to expand the u. What is u? U is just energy. Okay, m. How do you expand the v? V is actually this. This is velocity. Yeah, velocity is the displacement over time. Is L over T, right? Is mg. What is z? G is acceleration, okay? And z is of course L. Any distance, any displacement, any what do you call distance, displacement, or when it represents length, okay? It is L, right? In terms of primary dimension, okay? How do you do that? This is how you expand them, okay? In order to check whether this equation is homogeneous, right? In order to check that whether this equation is homogeneous or dimensionally correct, right? This is how you do it, fellas. Okay, I repeat, in order to check, if I ever ask you to prove this equation, whether this equation is valid, okay, is dimensionally correct, okay, that is the form of question I'm going to ask you, fellas. Okay, it refers to the same thing because dimensional homogeneity is to check on the validity of the equation. Okay, if I ever ask you in the question later on, try to prove that this equation is correct or this equation is valid. Okay, or try to check the validity of this equation. See, those are the form of question that I may be asking you, which is referring to the same thing, dimensional homogeneity. Okay, now how do you do this? How do you prove this? You're not going to tell them, okay, this one unit is joule, this one unit is joule, this unit is joule, this one unit is joule, so they are valid. It doesn't work that way. Okay, it doesn't work that way. One way of finding out is you need to expand them. Okay, just like what we did, okay, earlier on for force. Now you have to expand this. Expand the E. Oh no, expand the U, expand the KE, expand the PE, expand everything. Then you need to prove, okay, the dimension for this, dimension for this, dimension for this, and so on and so forth. Now, let's have a look at the answer. Okay. You have to expand all the equations, yeah? Okay, 1, 2, 3, 4. You have to expand all of them and then compare if they have the same dimension. Right, okay, you expand them. First, in order to expand, you need to know the definition of the energy. Now, if you notice, the change here doesn't matter. Okay, they take the change out. Like this triangular thing, they don't put it in the equation. Okay, they don't put it in the equation. Okay, they just write energy here. Okay, they just write U. U is okay, right? U is this is actually just U. Okay, forget about the triangular thing. Okay, the kinetic is mass over v square, and the potential is mgz. Right. Okay, for energy is defined as force displacement multiplied with length. I repeat, energy is defined as force times displacement. Now, force, I think we have developed force earlier on, right? I think in this slide, force and its primary dimension, okay, we expand the force into m and a, acceleration. Force equals to ma. Acceleration is length over time square. I repeat, acceleration is length over time square. So if you were to write it down in symbols, this is how it's going to look like, right? Write it down in symbols. This is how it's going to look like. So m, the mass, m, the length, t, and the time, small t, right? Mass m, length L over time square is t square. Okay, you have the force ready here, readily available. Okay, so have a look at this one. Energy equals to force time multiplied by length. Force has already been defined earlier. You just need to multiply by length. Add another L. So earlier on, you have force ml over t square. Now, if you multiply with length, it's going to be ml2 over t square. Now, your task, in order to prove the validity of this equation, you need to make sure that the rest of these equations will have the same primary dimension. Okay, we'll have this is what we call by the primary dimension, or the symbols of primary dimension. Okay, you have to make sure that everything will end up the same. I repeat, you have to make sure that the change of U, the change of KE, the change of E will give you the same ml2 over t2, or ml square over t square, small t square. Right, okay, let us move on to U. Right, the U here, okay, U is M, okay, U is the internal energy, is equals to M multiplied with U. Okay, M multiplied with U. Okay, forget about the minus stuff, right? Because the triangular, it doesn't valid, okay, in terms of primary dimension. Okay, just MU. This one is half mv square and mgz. That's it. You don't have to minus, because even if you minus, it's still going to give you the same thing. Okay, right. Have a look at this. U equals to mass multiplied with U mass. Now, you have energy, right? Okay, you have mass multiplied with the energy, which has already been defined earlier, divided by mass. So mass divided by mass equals to energy. So energy equals to delta U equals to this. So the first part is correct, right? So E equals to delta U is correct, okay, from its primary dimension. Okay, let's move on to the second equation, delta KE. Delta KE is defined as mass mv square. Delta KE equals to half mv square. Now forget about half, because half is constant. It's not going to give any values. Okay, it's not going to give any values. That is why they take the half out, because we are only concerned with the dimension values, right? Regardless of the constant in front of it is 0.3, 0.2, 5, 6, 100,000 millions. Okay, you don't have to worry about that. All the thing we have to worry is just the dimensions. Okay, the change of kinetic energy or just the kinetic energy equals to mv square. Now, define v square. V square. I think they jump around, you know. Okay, I'll help you out with half mv square. Okay, let's do it together. Okay, let's just do it together. Right? Let's do it together. Okay, where's my pen? Okay. Right. So what was it again? The kinetic energy, yeah. Okay, kinetic energy. The kinetic energy, or just the kinetic energy. Okay, I will penalize you for this. Okay, don't have to worry. Equals to half mv square. This is also okay. When we talk about a dimension, okay, we can throw this. This is constant. Okay, it does not give any value. It does not give any value for the dimension, so we can neglect this. Okay, we can take this one out. So m, okay, is already in its original form, the primary dimension. Now v is literally length over time. Okay, v is l over time. Sorry, l over time. Right? V is l over time. This is v, right? V is l over time square. So in this case, you have L, length is L. This one can be displacement, yeah? So we consider that as length divided by T square. And then you have this one L square. You have L square, you can write it down right away. So T square is T square. Right? So that is how they got this. Okay, that's how they got this. That is KE equals to this. M L2 over T2. Now, we have to check whether this one is correct or not. Okay? Is KE similar? M L2 over T2. Now, let's find out. M L2 over T2. Let's find out. Yes, apparently correct. K equals to M L2 over T2. Again, we have proven that KE equals to U plus KE, they are all of the same dimension. The same dimension as E, U, KE. Now, last but not least is for us to prove the potential energy is of the same dimension. Okay? Now, you have M, the potential energy is mg. Okay. Might as well just do this together again. Okay. Right, okay. The potential energy. The change of potential. Sorry, I'm sharing the wrong thing. All right, I'm gonna share the whiteboard. Okay, the change of potential energy equals to just potential energy. Okay, it can be as simple as that. Equals to m, g, and z. M mass g is the what is g and z?
Gravitation.
Exactly, the gravity or gravitational force, right? This is actually acceleration, fellas. Okay, is acceleration. Okay, z is L, is a distance, right? And then this one is m. Is also equivalent to, you can write this one down, yeah, is mgz, right? You can put it down as m a l, right? Just to make it simple, just to make it easier for you to see. Okay, just to make it easier for you to see. You have m in its primary dimension multiplied with a is primary dimension. No, this one you need to expand. A is actually velocity over time, right? Okay, so you have at m l. Okay, you have v. Now you also have this one. You can expand v over t. V over t is actually L over t, right? Or I think we have defined this. I think we did this together, okay, in a previous example, I believe. So V over T, this one is L over T square. It's length over T square multiplied with L, right? So you will end up getting L square, L multiplied with L, you get L square, L square over T square. You have L square over T square, right? Potential energy, after you have done all the calculation, after you have expanded them, this is what you will get in the end, ML2 over T2. Now it's time for you to find out whether they are correct. Again, they are correct. ML2 over T2. Although, okay, one thing for you to note is, right, one thing for you to note, although they give you the different equation, right? Although they give you the different equation, energy equals to force time length. Okay, energy equals to force times length, and then you have U equals to mass multiplied with the energy of a mass. Kinetic energy equals to mass V square, half mv square. The potential energy equals to mgz. They will end up giving you the same primary dimension, right? The same primary. This is the method for you to prove that this equation is valid, right? That this is the method. This is the method that you can use in order, okay, to make sure that this equation is valid, or this equation is dimensionally homogeneous. Okay, I could say that this dimension is now proven to be dimensionally homogeneous. All right? Okay. And another equation. Okay, this is the last one, I promise. Okay, this is the last one. We're not going to go through here, because if we go through here, nanti you muta. Okay, too much info. Okay, at the same time, right? This is the last slide, I promise. This is the last slide, right? Okay. Before we try doing some exercises later on. Right, okay, this is another equation. P plus half rho V square plus rho GZ equals to C. Now, I wonder if you've seen this before. Have you seen this equation before, fellas? Have you seen this equation before? Fellas?
Yes.
Yeah, you must have seen this
Yes.
equation before, right?
Yes.
It's one of the most important equation in fluid flow, fellas. If you tell me you've never seen this equation before or in your life, then something is wrong somewhere. Right? I can only say that something is wrong somewhere. Right? When I say that this is one of the most important equation in fluid flow analysis, trust me, I meant it. Right? You must have seen this equation. Don't tell me you've never seen this equation, because if you have never seen this equation, I give up. Right? Okay. This is very important equation in the study of fluid flow. Remember this well for the rest of your life. Okay. As long as being an engineer, you have to remember this. Right. Okay. Another equation that you can check, right, whether it's homogeneously dimensional or not. This is the type of the beautiful equation. Okay, if I were to task you to prove this, would you be able to do it, fellas? Now I want you to prove this to me, whether this equation is valid. That is my question to you. Now, fellas, to be frank, now tell me, if I were to ask you to do it now, would you be able to prove whether this equation is right or wrong, or valid or not valid? Would you be able to do it? Type in the chat box. I want to see. Would you be able to do it? If I were to ask you, right, if I'm challenging you, I need you to prove this equation to me that they are valid, that they are of homogeneously dimensional. Okay, you need to prove to me. Can you do it, fellas? Can you do it? Right? How's that sound? Okay. If my explanation is, I believe, is good enough, you will be able to understand. I strongly, you know what? I strongly urge you to understand this, because after this point onwards, it's gonna be chaos. Trust me, it's gonna be chaos. Right? It's gonna be chaos. All right? Okay. So have a look at this. Okay, let's go through this very quickly. What time is it? What time is it? What time is it? Ah, it's almost 9. Okay. Just this slide, right? Then we can try some exercises out. Okay, because I really want to give you your present at the end of this lecture because you've been good boy, right? I ask questions and then you answer. Ask questions, you answer. Right? Being good boy, I have to give you a present. Okay. Now have a look at this. P plus half rho v square plus rho gz. I want you to prove whether this equation is right or not. All right. Okay. Then prove it. How do you prove? Of course, using the same format. Then you have to show that each of the dimensions inside the equation is dimensionally homogeneous. Okay, you have to make sure that all of the equation term 1, term 2, 3, and 4, like the first part of the equation, first, second, third, and fourth, they must be of the same dimensions. That's it. That's the only thing that you need to do. Okay. You know what? I promise you, a question of this will definitely come out in the test. Right? A question of this will definitely come out in the test. Right? There's just nothing I can promise more. I can only say that this will definitely come out in the test. Okay, right? Because it's one of the most fundamental thing in this modeling chapter. Okay. You still need to do what you need to do is that you need to prove that each of these terms of the equations must be of the same dimension. Okay. So like this. Okay, just like this. Right, you have P, you have to make sure that P, the first equation, first term, second term, and third term must be of the same dimension. Now, here what you do. Okay, pressure equals to force divided by area. Okay, pressure equals to force divided by area, and you know that force F equals to ma. I think this is the first okay, force equals to ma. Okay, again we're moving back here. Right, this is the first slide. Force equals to ma. Right, okay, you all know where it comes from. Right, pressure is F divided by A. Now F equals to ma. Force m and a. A is the acceleration, and area is 1 over length square. Okay, is divided by area, right? Area is actually L square, is the length square or distance square, and you the distance, the primary dimension is length. Okay, you have to know that the naming, fellas. I think one of the difficulties is for you to for you to know this, right? Like I told you, you just need to understand the first 4. The first 4 is of utmost importance. Okay, just understand the first 4, I believe. All right. So force is mass length over time. I think we have defined this. Divided by area is length. Now, if you were to calculate this is what you'll get in the end. Is m over t2 square. Sorry, m over the time square L. What about the half mv square? Half rho v square is, okay, rho is mass over volume. And then you have the velocity, length over time square. And then if you were to expand this into its primary dimension, this is what you would get. Right? This is what you would get. So mass multiplied with the length square, volume is m3, right? Is L3 multiplied by time square. Now, if you multiply length, okay, power 2, power 3, cancel out, leave 1L, okay, L over T2. Okay, so you will get something similar, right? Just like rho gz. I think we did this, right? Rho gz, okay, rho gz is the mass, the acceleration, and the length, and you will get this in the end, fellas. Okay, so by looking at this, we can say that this equation is valid. I repeat, by looking at this, we can assure that this equation is valid. Right? Okay, I stop here. Time for question. Do you have any question? Ada soalan? Or you want to try the exercises first? Right? Want to try the exercises first, fellas? Then
Yeah.
you ask questions. Okay. Okay, I'm gonna stop sharing. Right. Go to the exercise right away. Okay. Right. I think you've done acceleration. Okay, just do it anyway. Right. Okay. I want you to write the primary dimensions of each of the following variables. Okay, give it a try, fellas. Okay, acceleration. What is acceleration? Okay, acceleration A.
Square over t squared.
A over
V over T.
L square over t.
Right. Okay, you can expand them in any way that you want. Right. But okay, let's try. Take out a piece of paper, fellas. Take out a piece of paper. Okay, take out a piece of paper. I'd like to expand all of this. Okay, angular velocity. What does it mean by angular velocity? Does anyone know? But this one, right? The angular velocity. This is the angular acceleration is angular velocity over time. Okay. Just give me a sec. Okay, just give me a sec. All right. Okay, I'm just gonna help you out a little bit. Okay, I'm just gonna help you out a little bit. Okay. Copy the question first. Okay, copy the question first. Right. Take out a piece of paper and give it a try. Right. Just please give it a try. Trying yourself is not the same as watching somebody try. You know what I mean? So you need to try. To be honest, you literally need to try. Give it a try. Okay, so this is the first one. Okay, write the primary dimensions. You don't have to write this. Just acceleration, angular velocity. Angular velocity is the angle. Okay, is actually angle over time. Angle over time. Okay. This one is this one over time. Right. If you don't know what it is. Okay, and this one, acceleration. Okay, acceleration is, you can follow the block length over time square. Okay, length over time square. So these are the definition. I'm helping you out with the definition values. So let's try this one out. Copy this one and try it out. And give me the answer in 5 minutes. Was you able to do that? Right, give me the answer. Okay, I want everyone to try and then give me the answer. Right? Because I'm literally gonna give you a quiz after this. Okay, after this, please do this one. Try to do this one. I will give you your quiz. Okay, you have to submit. Right, you have to submit as soon as possible. Okay, while I'm giving you a chance for you to try this one out. All right, and then we'll discuss the answer. Don't worry, we'll discuss about the answer. Okay, try it out. Try it out. In fact, I have some more that I want you to do as well. Right. Okay, I'm gonna add more. Okay, I'm gonna add more. Right. Okay. This one. Please, the specific heat at constant pressure. A, B, C, D, E, F, and G. Right? Define this. I want you to write the primary dimension for all of these variables. The specific heat, the specific weight, the specific enthalpy. Okay, I'll give you the definition. Okay, so that you'll do it faster. Okay, I'll give you the definition. Okay, so this one, the specific heat is energy per unit mass per unit time. Per unit mass and time. All right, mass and time. The specific weight. Okay, energy per mass. Sorry, per unit temperature. Apologies. Okay, okay, that's the definition. Specific heat is the energy, amount of energy released, absorbed. Okay, for a unit of mass, a unit of temperature. All right, the specific weight. Specific weight. Nah, this one is straightforward. Okay, is the raw energy, is the density and the gravity. I think you've done this, right? It's just the raw. Raw is what? Raw and G. Okay, the enthalpy as well. I think we did this. Okay, so you have to try this. I'll give you 10 minutes. I'll be back in I'll be back in 10 minutes. Well, I'll be back in 10 minutes. Try to do this one first, fellas. Try doing it. We'll share the examples, and I can assure you I'm going to give you a quiz. Okay, please try this one out. Okay, copy the question. I want you to share the answer. I'm going to read out names later on. Right, I'm going to read out names for you to give me answer. Okay, please try doing this. I need to know that you understand. Fellas? Now the moment of truth. Shall I get the answer from... So first off, are you ready? You all ready for the answer? You all done? Okay. Very easy, isn't it? Very easy. How did it go? Was it easy? Easy piece of cake, right? Was it piece of cake? Okay. Right. Now, okay, I have list of names. You want me to show the to share the answer, or you want to give your answer to me? Which one? Which one?
Yeah.
Right. Can anyone tell me what's the answer for the first one? The answer for the first one. If you don't know this, what's the answer for the first one? I think we did this right in the lecture notes. Okay, in the lecture notes. If you wonder where the lecture note is, please refer to your ELIP. I downloaded, I uploaded your lecture notes there, as well as some examples from the book. Right, some examples from the book that you can have a look. All right. So, what's the answer for the first one? What is the answer for the first one, fellas? Answer for acceleration, what is it?
L over T squared.
Okay, good one. L over T square. Okay, for the first one is L over T square. Right. Answer for the first one is L over T square. Okay. What about 2? What about B? The angular velocity.
1 over T.
Okay, what okay, angular velocity is 1 over T. Right? Is 1 over T. How about angular acceleration?
1 over T squared.
Okay. Right, 1 over T square. I'm just gonna stop here. Okay, I'll share with you the I'll share with you the right, the answer. Okay, if you wonder, right, how they got the answer, so this is the answer. Okay, acceleration. Okay, like I told you, you have acceleration, angular velocity, and angular acceleration. So the acceleration, the A, is velocity over time. Okay, velocity over time, right? It depends on it can be many ways of expressing this. Okay, you can have velocity over time, you can have length over time square. Is up to you. Okay, it's up to you. So the moment you have like define everything is L over time multiplied with 1 over time. This is what you get in the end for acceleration A. So you have L over time. For angular velocity, the omega here, primary dimension or angular velocity equals to angle divided by time. Now, tell me, is angle one of the primary dimension, fellas? Is angle one of the primary dimension?
No?
Okay.
You sure? Are you sure? Angle is not part of the primary dimension.
I'm sure. I'm sure.
Very sure? Right? How do you compare angle and displacement? Angle and displacement. Now tell me. I want arguments. I want to hear your arguments. For displacement, we define it as L. Why angle is not defined as L?
Because it's
Because-
not linear movement.
Because this one could literally be, because we're talking about displacement here, okay, but in angular, in an angle, right? Then if we discuss about displacement, then it should be length over time. Why doesn't it? Why don't it?
Because it's not linear displacement.
Okay, that's for you to ponder. All right, that's for you to find out. All right, okay, if this is how you define the angle, okay, we are going to assume that angle as a constant in this case, so it is 1 over time, right? It is 1 over time. Is the answer from the book anyway. All right, okay, I'm just right, I'm just asking you to put your thinking cap for us to discuss about it. Right, and angular acceleration is even easier. It's just this 1 over time, that's it. Angular velocity over time. In fact, I've given you all, so it's quite straightforward. Okay, I wonder. Now, T2, sorry, the rest of this, you have the specific heat, specific weight, as well as specific enthalpy, and this is the answer. You have specific heat, specific weight, and then the specific enthalpy. So you have this specific heat is energy of a mass temperature. This is how it is defined. Okay, so energy is ml2 over T2 divided by mass multiplied by temperature. This, okay, if you notice, now in this case, you have the 4 primary dimensions, fellas. Okay, I repeat, in this case, you have the 4 primary dimensions that we talked about earlier. Right? You have mass, you have length, you have time, and then you have temperature, if you notice. Okay? I think as far as your question is concerned, maybe we'll just limit it till here. Okay, we'll just limit it till here because we're not going to touch on the candela. We're not going to touch on the mole, right? The number of amount of matter and amount of light, right? Okay, so I would stress more on the first 4 primary dimensions. Okay, just like being shown here, right? So you have ml2 over square. Okay, the energy, which we have defined earlier in the exercises that we did, even in the lecture notes. And then you have mass and temperature, which you can get directly. And then for the specific weight is rho g. Rho is mass over volume and gravity is length over time, square. All right, this is acceleration. G is acceleration. So it's like rho a. So you have them. Okay, so it's quite simple. And then the specific enthalpy. This is specific enthalpy is h, small h. The small h, meaning enthalpy per unit mass. So enthalpy per unit mass, I think we did this, right? I think we did this earlier on, okay, in the lecture notes. So you must not have gotten this one wrong. Okay, it's the energy per unit mass, ml2, okay, it's the energy divided by m, so you have this in the end. All right, so that would be it. Now, are you ready for your present, fellas? Right? From the confidence I'm saying, you are very confident, okay, which is good. Right? You're confident, which is good. Now is the time for you to show it off. Okay? From the confidence, yes, good. Okay? I'd like to take your burning tenacity at this point, okay, to do this question that I'm going to post in ELIP. All right? Now, allow me to share with you the now, if you go to your ELIP now, first off, when do you want to submit this quiz? When do you want to submit this quiz, fellas?
By
When
today.
do you want to submit the quiz? Before 10? Would that be okay?
Yeah.
I need opinions. Come on. It's negotiable.
Sir,
Yeah.
can
Before 5.
the quiz submit later this evening?
And your reason?
Because I'm on my way back to Unimas actually.
You are back to the mouse. Okay.
Yeah, I'm
Right.
sorry, sir. Yeah,
That is not a very good reason. I need more.
yeah.
So anyone else supporting her? Anyone else supporting her saying that the quiz should be submitted later on? Anyone else?
Does the quiz require a lot of time?
A good question. A very good question. It depends on your what do you call it? On your understanding of the exercises, right? Because you're confident enough saying this is good, is cool, is no, it won't take time. If I were to do it, I can do it in 5 minutes. I can do it in 5 minutes. Okay. If I were to do it, okay, you have 2 questions. Okay, you have 2 questions. Okay, one question, 15 minutes. Okay, one question, 15 minutes. Then you have half an hour for you to do it. Actually, you can finish at 10. Right? Actually, you can finish at 10. But I'm being generous today. Right? I'm being generous today. Right? I'm a good guy. Right? I'm going to give you some more time. Okay? I know that there are some of you who still don't understand yet. Okay? Still don't understand yet. Right? Please revise back. And then if you refer to your ELIP, I'm giving some exercises from the book, okay, which is quite simple for you to understand. In fact, we covered them. Okay, we covered them. 7.2 we covered them. 7.1 is very straightforward, just like the exercise that we did. Okay, just like the exercise that we did. Okay, have a look, and then the quiz itself is the application of what we study. Is on dimensional homogeneity. Okay, I'm gonna give you until 12 today. Would that be all right?
Okay.
You don't want it?
Because there are some
Yes, sir. It's alright.
Okay.
yes.
Yeah, I want response. Okay, I need to hear response. If I don't hear any responses from you people, we submit at 10. So how's that sound?
Morning, doctor.
Oh yeah, okay. So you cool, yeah?
Can
Yeah.
Yes, class from 10 to 12.
Yes.
You have class from 10 to it does not matter. My class is until 10.
I see.
All right. My class is until 10. So I have all the power, okay, to use you until 10. You cannot run away.
I'm not sure.
Right.
I think
Right? But I need more responses. Do you agree with me saying that you should submit before 12 tonight?
Yes, sir.
Yes,
Yes.
sir.
Yes, sir.
Yes.
Yes,
I want a
sir.
lot more yes.
Yes.
Yes,
A lot more
sir.
yeses.
Yes, sir.
Yeah, tonight. Yes, 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 yes.
Yes, yeah?
Yeah.
Right. You sure?
Yes.
Thank you, sir.
Right, okay. Right.
No, sir.
Until 12 it is. Okay, until 12 it is. But although I say that you have to submit until 12, try to use this half an hour. This half an hour that we have left, I want you to do it. Right? With the information still fresh in your mind, try doing it. Right? Okay, try doing it. I told you it's an open book, a quiz, right? It's actually a question that I made up myself. Okay, a question I made up myself. You won't be able to find a book. Right? You won't be able to find a book, trust me. Okay, so I'm gonna give you until 12 tonight, right? For those who are still driving, drive carefully, right? Don't ever drive again in my class. Okay? Drive carefully. I'm gonna give you until 12. Okay, until 12, just today. Meaning you have until 9:30 until 12 at night, not in the afternoon, at night. All right. So you have time for you to go back to the lecture. If you don't understand what I said, have a look at the exercises. Have a look at the examples. All right. Okay. And then discuss among your colleagues, among your members, if you don't understand. Okay. I want you to submit the quiz before 12 today. Right. I am going to enable the quiz now. You can access the quiz, and then I want you to submit before 12 tonight. That would be it. Okay, that would be it. Right, I've enabled it, right? And then for those who have not taken your attendance, please take it now. Right, please scan your attendance. And I want you to submit your quiz. I actually want you to submit the quiz right away, but okay, I'm going to give you some more time. Okay, because I want why I'm giving you this extra time for you to do it, because it's very important. The next part of the lecture would be disastrous, you know, if you don't acquire the concept, like literally acquire the concept. All right, scan your attendance. If you would like to acquire manual attendance, please let me know, type in the chat box. So I believe that will be it for the lecture today. Do you have any questions?
Sir, I would like to ask, is it the bracket is compulsory for the equations?
Bracket.
Yeah, is it compulsory in the equation?
Okay, just I think in terms of uniformity of your answer, I would say just put bracket in. Just do it the way the book is suggesting you to do it. Right? Do it in the form of just like the way the book is doing it. You can do it simpler, but then again, I'm just afraid it's going to be messy. Okay, just do it the way like the book is doing. Okay.
Okay, sure, sir.
Mhm. Any more question? Okay, so if you don't have more questions, I'm just going to leave you with the exercises. Please try doing them. Okay, please try doing them. Please try to understand, because this is one of the most important part of the lecture, right? Okay, this is the most important part of the lecture. Okay, that will be it. Thank you very much for joining me this morning. Okay, for joining me this morning. I wish you all the best for your quiz. Enjoy your quiz. Okay, so I think we on Monday we're not going to have any classes, right? On Monday, because it's public holiday, so we shall meet again on Friday, right? We shall meet again on Friday, 8 or 8:30, fellas. 8 or 8:30. Shall we start at normal 8, or you want 8:30? Because a lot of students are still not in. When it's 8, right? I'm going to give you some time for you to get ready. Okay, 8:30. So shall we meet at 8:30 next class?
Okay, Doctor.
Yeah, sure, sir.
Yes, Doctor.
So we shall meet at 8:30
Yes.
on Friday class, right? Of course, when we have Monday, I'll try to balance it. I'll try to balance the time so that we can have longer lecture on Monday as well as on Friday. Okay, till then, I'll be seeing you again. Okay, hoping the best for you people. I'll be take care, and I'll be seeing you again in the next class, inshallah. Okay, we'll see you again. Till then, bye bye.
Thank you, Doctor.
Have a nice day,
Yes,
Doctor.
sir.